morning. I am Karen Kok, I'm from Unisia High School, and today we will be doing revision on chemical equilibrium, the theory behind it, as well as calculations involved. So I'm starting with just indicating that the graphs and examples that I'm using in my lesson, they are from Oxford Successful Physical Sciences for grade 12, just a reference there. And to start off with, just some concepts. What is an irreversible reaction? Because up to the point where we've started dealing with chemical equilibrium, you've basically only been exposed to irreversible reactions. And in an irreversible reaction, the concentration of your chemicals start at a high point, and then it decreases until the concentration of your initial reactants is zero, and the reaction then stops with the concentration being zero. Now, in dealing with reversible reactions, we say that a reaction is reversible when the products can be converted back to reactants. So this is just writing it in general. Reactants form products, products form reactants. So for example, if reactants are A and B, they form C and D. And this can then be broken down into two separate reactions, A and B forming C and D, being the fourth reaction, and then the reverse reaction, C and D, breaking up and forming A and B again. And now the graph changes. Right, so the graph for the reversible reaction looks like this. We start off with high concentration of reactants. This is now A and B forming C and D. This is what happens to the reactants. The concentration decreases. Initially, we start with zero product, but as the fourth reaction occurs, the product concentration increases, and then eventually it also becomes constant. On this graph, there is no point where either the products or the reactants concentrations get to zero because this reaction goes into chemical equilibrium. Now, to illustrate the chemical equilibrium, I want to show you just a small demonstration on cobalt chloride complex reacting with water to form this complex and chloride ions. Now, if you are asked questions on this reaction in exams, you would not need to know this off by heart, but it should be given to you. You just need to be able to predict what is going to happen. Now, compared to this one, we've got the reaction between iron and hydrochloric acid. As you can see, it's not reversible. We get iron chloride and hydrogen gas, and because this hydrogen gas can escape, it means if you do this in an open container, it is not a reversible reaction. You cannot compress hydrogen gas and iron chloride solution and hope to end up with iron filings and hydrochloric acid. So that reaction is not reversible. Now, to illustrate this reaction with the cobalt chloride and cobalt complex, we are going to look at the change in factors and how the change in factors affect the visibility or what is visible in this equilibrium system. So I am starting off with cobalt chloride, the blue one. Right, and as we can see in this balanced equation, I'm now going to add a few drops of water. In my hand, I've got cobalt chloride, the blue one, and as you can see, I'm now going to add a few drops of water. Let's just add it drop by drop. We don't want to add too much. As you can see, there is a gradual change, maybe one last drop. Clearly, color change. Here we go. So what I've now done, I have added water to cobalt chloride, and there's the color change to pink. And what I'm going to do now that I've got the pink solution, the pink complex, I am going to add a few drops of concentrated hydrochloric acid, and again, an immediate change in what is visible. It changes back to the blue one. And I can continue doing this the whole day. Because I'm busy with the chemical equilibrium here, it goes in different directions depending on what I'm adding. Now, I'm going to take the blue one again add water until it turns pink. And then what I want to do is place it in hot water and see whether the hot water will have an effect on the system. So let's just go turn it into the pink one. All right, seems like the blue is gone. And we put it in boiling water, or rather not in boiling water, a container with boiling water. And as you can see, color is definitely turning into blue. If we wait long enough, it'll go to blue. I did not add any chemicals now to get it to blue. I simply put it in the hot water, the blue solution again. Let's see if ordinary tap cold water will have a quick effect on it. Yes, I can see the blue color is going away, turning into pink. As you can see, definitely reversible reaction depending on the factor that I am adding to it. And this is something that you need to be able to explain in exams. Right, back to the theory. This is the system that you've been given. As you've seen, I've added water, the blue solution turned pink. I've added concentrated hydrochloric acid, the pink solution turned blue. And we've got the delta H value for the system. I have heated up the pink one, it turned blue, and when I put the blue one in cold water, it turned pink again. As we said, this is what this work is all about. So here we've got, just to start off with the basics, 3 containers, and the question is which ones here will represent a closed system or an open system. Our previous example of iron filings with hydrochloric acid, or as we've got here, zinc with hydrochloric acid. Which one is open or closed? This one is definitely an open system, because in this reaction we are going to get hydrogen gas being formed and hydrogen gas will escape. If you put the same chemicals in a container that's got a lid on it, it is a closed system, but it's still not a reversible reaction. And then here we've got 2 chemicals, silver nitrate and potassium iodide that have reacted. They've formed potassium nitrate and silver iodide. They're all in the same container. They're all either solids or solutions. They do not escape. This is also a closed system. Here, just another way of representing an open system and a closed system. In this one, we've got an open system because the water particles are able to evaporate and escape into the atmosphere. So that is an open system. In this one, there's been a beaker placed over a container placed over the beaker. So the water molecules may evaporate and they may condensate, but they all remain within the same system. Therefore, that would be a closed system. Now, chemical equilibrium. The illustration that I've got here was given to us by the Free State Department of Education a few years back. So sometimes it's just an easier way to remember this. They say there are 2 floors of a store. They're connected by an up and down escalator. Floor 1 has 7 people, floor 2 has 12 people, and there are always 2 people occupying each escalator. So just showing you what they've got here. Floor 2 with 7, maybe we need to say 7 groups of people. Floor 1 with 12 people, always 2 people on the escalator. So if you can think of this as a chemical system, it simply would mean that if 2 people are going up all the time and 2 people going down all the time, it means that the people on a floor will vary. They're going to change. But the number of people on the floor will not change. Always the same number, but always changing. And this is what we've got in a chemical system. So the definition for chemical equilibrium, it is a dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Now I've got a very simple illustration that I want to do, and this is, for example, if we would say hydrogen gas reacts with iodine gas and it forms hydrogen iodide, and I've represented the hydrogen as those black spheres and the iodine as the red ones, then when they react, what would happen is hydrogen would break up, iodine would break up, and they would form new bonds. So that would simply be the reaction. Now, if I want to illustrate chemical equilibrium, it would mean that the moment that one of those molecules and one of those molecules break up, then for the reverse, simultaneously, two of those would also break up. These two would form another diatomic one, whereas those would now form the hydrogen iodide one. So that would now be chemical equilibrium at the same rate, but not necessarily the same amounts of each type of chemical. After some time, the system reaches dynamic equilibrium. It stops producing more products, even though there are still reactants left. So the concentration of the reactants and the concentration of the products remain constant. As you can see, we've already had this graph earlier on. We start with a high concentration of reactants. It lowers until a point where the concentration remains constant. We start off with no products, and then their concentration increases until a point where the concentration is constant. The forward and reverse reactions are at equilibrium when the two curves meet and become horizontal. Now, compared to the previous graph, look at the previous graph. This represents concentration. In other words, the amount of substance in mole per cubic decimeter. Start off with maximum amount of reactant, zero product, and eventually they remain constant. Now compare that to the reaction rate graph. You start off with a high rate in the reactant, no rate in the product. And then the reaction rates drop for the forward reaction, it increases for the reverse reaction, and it reaches a point where the rates are equal, and this is what we've said. This is chemical equilibrium. The rate of the forward and reverse reactions are equal. Now, to explain what I've illustrated to you, and also in all the questions that will follow, we work with the French guy, Mr. Le Chatelier's principle. And he said, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Now, we're now going to deal with the different factors. And this is all that you need to answer the whole time. You need to figure out what was the factor that was disturbed, what can the system do to reinstate a new equilibrium. And the what will the system do is an easy question to answer because there are only two options. Will the forward reaction be favored or will the reverse reaction be favored more? So, first factor affecting the position of equilibrium is the change in concentration. So we're going to work with an example, and our reaction that we're going to discuss throughout now is this one of nitrogen dioxide to a mole of nitrogen dioxide being in equilibrium with dinitrogen tetroxide. And the reaction, as you can see, the forward reaction is exothermic. If we look at the two possible graphs that can be drawn, The one for rate, it doesn't matter at what value the fourth reaction starts. It always starts at the maximum value, and then it lowers until it reaches equilibrium. And at this point, the rates of the two reactions will be equal. And then with the amounts, the amount of mole, let's say you started off with 4 mole of the reactant, it becomes less, and the amount of mole of your product becomes more. Now, the question is, what happens to the rate of the reaction, and in which direction will the equilibrium shift for each of the following changes? And we are now, to this system, we are now going to add NO2. Now remember what Mr. Le Chatelier said. You need to get rid of this extra factor. And we've been adding NO2. So if I look at my system, adding NO2 means I am adding reactant. One of two things can happen. Either the fourth reaction goes faster or the reverse reaction goes faster. So which of these two reactions will go faster? Of course, the one that will use up the extra NO2. First thing that happens, both reaction rates increase because there are now more particles. And the reaction that is favored is the reaction to the right. Why is the reaction to the right favored? Because the reaction to the right uses up NO2, and that is what we want to do. We want to get rid of the extra NO2. So what happened to our original graphs? If we look at the reaction rate graphs, this was now at equilibrium. Remember, we've added or changed the factor after your system already was at equilibrium. So at equilibrium, what was done? Now you need to be able to get a graph like this and say what has happened. So if I look at this, immediately the rate of the fourth reaction picks up a lot. The rate of the reverse reaction also picks up. Now remember, if you add NO2, you are adding more particles. More particles means more effective collisions. So more effective collisions means higher rate. Your fourth reaction goes faster. The reverse reaction goes faster, but not as fast, because the fourth reaction is the one that had to go even faster. And then that rate drops until we reach new equilibrium. If we look at the concentration graph, what's happened? Our NO2, amount of NO2 was increased, and then it becomes less, less, less until it is constant. The amount of N2O4 will then also increase because the fourth reaction increased until, again, equilibrium has been reached. Right, next factor. Now, NO2 is removed from the container. So let's quickly think what must happen. If NO2 is removed, you've now got less reactant. So the system wants to make more reactants. So now the reaction rate decreases. Why? Because there are fewer particles in the reaction vessel. So your reaction rate drops. The equilibrium is now favored to the left. Why to the left? To make up for the NO2 that was removed. Now our graphs must show that. So if we look at the reaction rate, both rates will drop because there are fewer particles. The NO2 has been removed. Therefore, your forward rate drops more because there are fewer reactants. Your reverse rate also drops, but not as much, and then again, equilibrium is established. If we look at the amounts, NO2 was removed, an immediate drop in the amount of NO2, and then it increases gradually until equilibrium. N2O4 rate also drops because the forward rate dropped, and then again reaches equilibrium. So that deals with concentration. Now, if we change pressure. Now, an increase in pressure is they usually express it that you increase the pressure by decreasing the volume. So remember now what happens. if the same number of particles are now limited to a smaller space. That means they are in contact with one another much more frequently, so that would mean many more effective collisions. Therefore, your reaction rate in general should increase. The system, however, wants to get rid of the increase in pressure. Now, how will the system do that? When we discuss an increase in pressure, we discuss number of particles. So if you want to decrease the pressure, it means you need fewer molecules. And to determine which reaction goes along with few molecules, you need to look at your equilibrium reaction and at the balancing numbers. So in our balanced equation, we've got 2 mole being in equilibrium with 1 mole. And that then means that the forward reaction is favored more. And if the forward reaction is favored more, my graphs change in this way. The reaction rate of the forward reaction picks up immediately. Your reverse reaction rate will also increase because there are more collisions, and then they both then join up again to form a new equilibrium. If my forward reaction rate increases, it means that the amount of product molecules increases, and accordingly, the amount of reactant will also increase until equilibrium has been reestablished. The opposite is true. When we decrease pressure by increasing the volume, now it means that the same number of particles now have got much more space in which they can react. And because there's more room, it means that there are fewer collisions, and therefore the reaction rates of both reactions will decrease. The system, however, needs to respond to change the factor, so it wants to increase the pressure. And how will it increase the pressure? It will increase the pressure by making more particles. So which reaction makes more particles? If we look at 2 mole in equilibrium with 1 mole, it means that your reverse reaction makes more particles, therefore the reverse reaction is favored. The graphs correspondingly then, for the reaction rate, both rates drop, but your forward rate drops more, because the reverse one is favored more. And if your forward rate drops more, it means that the N2O4 amount becomes much more less than the amount of the chemicals in the reactant. Next factor, change in temperature. Now, you are all familiar with an exothermic reaction, work that we've done in grade 11. An exothermic reaction releases heat to the surroundings, and there are 3 ways in which you can be informed that a reaction is exothermic. They either tell you chemical A and B form C and D and heat, which is part of the product. Or they can tell you chemical A and B form C and delta H is less than 0. Or they can tell you A and B form C and delta H, and now they give you a value with a negative number, which tells you it is less than 0. And you will remember this work from the work on reaction rate, where this value actually comes from the potential energy graph with time, as time proceeds, and my graph looks like this. And this is then delta H final minus initial, which would give us a negative value there. And then similarly, for an endothermic reaction which absorbs heat from its surroundings, so it can be written as reactant A and B needs heat as well to form C, or A and B form C, delta H is greater than 0, or A and B form C, delta H being positive, and then of course our potential energy curve then looking like this, where you add up at the higher energy state than where you started off from. So if the forward reaction is exothermic, then the reverse reaction is endothermic, right? something that you, I'm sure, are familiar with. So now, because we now know about that, we now need to look into the change in temperature. How will change in temperature affect our equilibrium system? So first of all, if you increase the temperature, this is my chemical reaction. I cannot answer a question on temperature if I do not know about the delta H value or the fact that heat is either added in the reactant or in the product part of the reaction. So the first thing, when there's a temperature increase, the first thing I have to know is that both reaction rates will increase. Why is this? Because you will remember the definition for temperature, the average kinetic energy of the particles. So if your particles have got more kinetic energy, it follows that they will collide more often and that there will be more effective collisions per unit time, and that means that the rate increases. So now, the reaction that will use up the extra heat is favored more. Both reaction rates increase, but one will increase even more. Which one is that? That is the one that can use up the heat. Now, if I look at delta H here, being negative means my fourth reaction is exothermic. An exothermic reaction gives off heat to the surroundings. It does not want heat. It's difficult to give away heat if it's hot around you. So that means that the endothermic reaction is favored more. The reverse reaction is endothermic, so the reverse reaction rate will increase more. And my graphs will then change like this. Both rates go up. Look at this. This is the first graph where we've got both rates being affected so much. Both rates increase. Which one increases more? The reverse one, N2O4 turning into NO2. And that one also increased, but less, and then they go back into equilibrium. Now, if your reverse reaction rate is favored more, it means that you are going to get much more NO2 and that your product will be used up, so the amount of N2O4 will drop. Opposite reasoning, when there is a decrease in temperature, both reaction rates drop. The particles are moving more slowly, so they collide less often. The reaction rate that works better in colder temperature is favored. The reaction favored by a decrease in temperature is the exothermic reaction. The fourth reaction is exothermic, so the fourth reaction rate is higher. So what's going to happen? Both reaction rates drop. Your exothermic one is the one that's favored more. So the fourth reaction, so your exothermic one is least affected, and your endothermic one drops more, so that rate drops further down until they reach new equilibrium. If we look at the concentration-wise, your N2O4 concentration increases and your NO2 concentration decreases. And that then brings us to the last factor, and that is adding a catalyst. Now, once more, if you think back of your potential energy curve that you've done in grade 11, if that is the shape of the curve and we are adding a catalyst simply does that. So a catalyst lowers the amount of activation energy, and it affects the forward reaction and the reverse reaction with the same amount. And that is why adding a catalyst speeds up both reactions in exactly the same way, and then they proceed at a higher rate, so it doesn't affect one reaction more than another one. The common ion effect, this is an equilibrium system in which we've got a solid that is in contact with its saturated solution. And equilibrium has been established. And now there are, again, factors that can affect it. If they give you delta H values, then you can reason about temperature. You will not reason about pressure here because these are not in gaseous state. I could now add hydrochloric acid. So now the question is, if I add hydrochloric acid, how has that got an effect on the system here? But we need to keep in mind that hydrochloric acid is a strong acid. And being a strong acid, we know that it ionizes almost completely, which means I'm in effect adding hydrogen ions and chloride ions. And my equilibrium system will recognize what is in common. So the hydrogen ions won't affect my system, but adding hydrochloric acid means I am in an indirect way adding chloride ions. And if I add chloride ions, I know the reaction that will be able to get rid of this extra chloride ions. That reaction will be favored. Therefore, the system will respond. Your reverse reaction is favored more, and you will see more precipitate. In other words, in your visible reaction, your little pile there should increase in amount. Same question here. When calcium hydroxide is added to water, the following reversible reaction reaches equilibrium. So again, we've got the solid calcium hydroxide ionizes into or rather dissociates into calcium ions and hydroxide ions. Explain what will happen if a few drops of concentrated sodium hydroxide are added to the solution. So if I now again remember, sodium hydroxide being a strong base will dissociate into sodium ions and hydroxide ions. And if I then look at what these two have in common with my system, I know that it's the hydroxide ions. So once more, in an indirect way, I've increased the concentration of hydroxide ions. So Le Chatelier's principle to get rid of the extra hydroxide ions, the system is disturbed, and the system will respond by favoring the reaction to the left. And once more, the calcium hydroxide amount will increase, and that would be our visible effect. Right, so here is a possible question, and I'm not going to deal with all of them. I just want to point out that you should be able to answer questions on, we've got the system of nitrogen gas reacting with hydrogen gas giving ammonia gas. Now, we could add nitrogen, we could add hydrogen, we could add ammonia, we could remove them, we could increase the temperature, we could decrease the pressure. All of those questions that we've already answered. What I want you to be on the lookout for is that a question like this is now specifically asked for the concentration in nitrogen. But we can also have a question where they ask the amount of nitrogen or the amount of hydrogen, and the concentration and the amount does not necessarily always give you the same answer. So we need to be on the lookout for questions like that. Okay. Right, I want to point out two questions that seem very similar, but they really are not. And that is the question on amount and concentration of chemical. So we've been given this equilibrium system, nitrogen gas reacting with hydrogen gas forming ammonia. And it says there's an increase in pressure by decreasing the volume. What is the effect on the amount of nitrogen, and what is the effect on the concentration of nitrogen? And sometimes the answer is the same, but they are not always. So let's just look at this specific one. So if we increase the pressure, now to discuss the full Le Chatelier's principle, an increase in pressure means that we are decreasing the volume. That means that the particles are closer together. So the system wants to respond by making the particles move further apart. And how does it do that? It favors the reaction that makes fewer particles. And if I look at the balancing numbers here, I've got 1 plus 3, which is 4 mole of particles that are in equilibrium with 2 mole. So in this system, the forward reaction is favored. And if my forward reaction is favored, it means that N2 turns into NH3. So what's going to happen to the amount of N2? The amount of N2, in other words, the number of mole of N2 will decrease. because the fork reaction is favored. Now, what happens to the concentration? So let's look at our formula for concentration. Concentration is N over V. Now, a simple way of actually figuring out what the change is to now assume that the size of my letters represents amounts. So I am now changing the N. What happened to the nitrogen now? The amount decreased. So now I'm making N smaller because the amount is less. But what happened to the volume? The volume was also decreased. That means V is also smaller. And the two will happen in the same proportion. And if the two happen in the same proportion, it means that N over V is still the original. So your answer to the concentration of N is that it's going to stay the same. Just be on the lookout for those possible questions. Right, we now get to the actual calculations involved with chemical equilibrium, and this is calculating the equilibrium constant. So just to start off with, what is the equilibrium constant? We calculated it by looking at the concentration of the products divided by the concentration of the reactants. But if you write this in the exams, you're not going to get any marks. So don't even go there. We just need to keep in mind that that is what we are dealing with. So here is a question. Write down the equilibrium expression for the following reactions. And the first one is the one that we've just had with N2 reacting with H2, forming 2NH3. So if I want to write this chemical reaction, Kc is equal to the concentration of the product, and the product here is NH3. And remember, we said we use square brackets for concentration. The balancing number is a 2. The balancing number becomes the exponent divided by the concentration of nitrogen, the balancing number being a, no, there's just one. Sorry, there's no balancing number there. And then that's a mistake there. And then hydrogen being H2 and the balancing number being a 3. Remember, the formula stays intact. The numbers that make up the formula, neutral formula, don't play a role here. It's only the balancing numbers that become the exponents. I'm sure you're all aware of that. So just information obtained from the Kc. Keep in mind the Kc value is temperature specific. The moment that the temperature remains constant, it doesn't matter what other factors you change, Kc value will remain constant. But the moment that temperature changes, the Kc value has to be affected. Interpreting Kc values, for Kc greater than 1, the formation of the products is favored. The equilibrium concentration of the products is greater than the equilibrium concentration of the reactants. Then when Kc is less than 1, the formation of the reactants is favored. The equilibrium concentration of your reactants is greater than the concentration of your products. So as they increase, showed here, if the concentration of products increased, then Kc increases. If the concentration of your products decreased, then Kc decreases. Right, we get to one calculation on chemical equilibrium. This is the one that was asked last year in November. And you will see immediately, without even reading, that there are two equations, which means definitely a multiple calculation one. Also, if you look at the amount of marks, 9 marks, and this is the latest trend that they give you a question that hasn't got any sub-questions that actually lead you into where you're supposed to go. Now, usually, I do not want to say always, usually our calculation starts at the end equation and then we work our way back up. So let's just read carefully, and the best advice I can give you is write down the values as you read along. So hydrogen gas H2 reacts with sulfur powder according to the following balanced equation, H2 plus S giving H2S. It's exothermic. It tells us the system reaches equilibrium at 90 degrees Celsius. That does not really affect what you're going to do, except that you need to be on the lookout for questions where they may then later on tell you, now the temperature is something different, because then your Kc value will change. Okay, so initially, 0.16 mole of H2. So initially for that one, we have added, or we've added into the system 0.16 mole of H2, and then excess of S, which means there's more than enough S for this reaction to take place. They sealed in a 2 cubic decimeter container. The system is allowed to reach equilibrium. An exact amount of lead nitrate solution is now added to the container so that all the H2S present in the container at equilibrium, all the H2S at equilibrium. Now, this is something to keep in mind. They may give you whatever values. You cannot substitute the values in your formula if it's not values at equilibrium. I'm now specifically talking about the Kc formula. Okay, so it's converted to lead sulfide according to the following reaction, and now they tell us the mass of lead sulfide is 2,39. So for this one, we've got 2,39 grams. Okay? And the question asks, calculate the equilibrium constant. So the question asks, what is Kc for that reaction? Okay, we cannot calculate the Kc for this reaction anyways, because as you can see, this reaction is not reversible. And we have to have a reversible reaction at equilibrium to be able to calculate Kc value. So I have to start at my final equation, for which I've got the value that 2,39 grams has been formed. Now I'm back at what I said before. Whatever you're given, try to convert to amount of mole. And I can do that. So for lead sulfide, and the reason why I put the subscript once more is to just help the examiner as well to see what your thinking processes were. Is mass over molar mass. The mass given was 2,39. You'll have to calculate the molar mass of lead sulfide. You look it up on the data sheet, 207 plus 32, which gives us 239 gram per mole. That is then substituted into there, 239, and that gives us 0,01 mole of PBS. So for this one, I've got 0,01 mole. Okay? Now the question is, so what? I can do nothing with the PBS, but my reaction is with H2S. What H2S is this? This is what I had to remember, is that all the H2S that was present at equilibrium. So I now know I had 0,01 mole of PBS. And the number of mole of PBS is equal to the number of mole of H2S. Why is that? Because the ratio is 1 to 1. And that means that the H2S is also 0,01 mole. Now, what H2S is this? This is the H2S that was present at equilibrium. Now, I find it easier to do the Kc calculations by using a table. Everybody does it in their own way. It just, to me, it seems as if it's an easier way to sort all the data. And what I can suggest is that if you do use the table, that you will use your balanced equation as the headings of the different columns. So we've got H2 plus S giving H2S. Let's just see in our balanced equation, yes. And it's necessary to add the states so that you'll remember we do not use the solid state for our calculation. So each formula in the equation is a heading in my table for a column. I've got one extra column on the left-hand side, and my different rows in my equation, I use the girl's name, Sue. This means this is the chemicals that we started off with, and I'm using the mole unit. This is what was used of the reactant or formed in the product, and once more, I'm working in mole. This is at equilibrium, so this is the row that we will be using for our calculation. No, I lie. This is the mole row. We use concentration in our calculation, but this is the row of values that we're interested to get our calculations. And then the next row is the concentration one. For the concentration one, we will use this formula, and I can already substitute the volume value because that is usually given in my question, and at the very beginning they said that we are working in a 2 cubic decimeter container, and remember they also said we've got 0.16 mole of H2 that was initially entered into the system. So 0.16 was initially entered, the volume is 2, and I've got one other value, and that is at equilibrium, the amount of H2S was 0.01. So at equilibrium, the amount of H2S was 0.01. Now, this is the row that works with the balanced equation. So this is the one that works with the balanced equation. I know on my product side, this is what gets formed, and this is what I will then have at equilibrium. Now, most of the times, not always, most of the times, you do not start off with product. You've got no product. Then whatever gets formed will give you what is at equilibrium. On the reactant side, you start off with reactants, and whatever has reacted or been used will give you what is left over at equilibrium. And I need a value at equilibrium to be able to complete my table. So I had 0.01 mole of H2S at equilibrium. That's what we've calculated. So how much had to be formed to form 0.01? The amount that had to be formed would be 0.01. I'm not filling anything there because I'm not interested in the sulfur. I need to go here. If 0.01 was formed, then in a ratio 1 to 1, it means that 0.01 was used. And that means at equilibrium, I'm left over with 0.15. To calculate Kc, I need this row, the concentration row. And the concentration row takes that value and divides it by 2. So we've got 0.15, which we have to divide by 2. That gives us 0.075. And on this side, we get 0.01 divided by 2, and that gives us 0.005. And now to calculate Kc, it is the concentration of the products in gaseous state divided by the concentration of the reactants in gaseous state. So that would be 0.005 divided by 0.075, and that gives us a value of 0.067, and that was then the answer. Right, so this concludes our session on chemical equilibrium. You've been given handouts by the department. Need to go and work through those calculations to ensure that you can answer a variety of different ways of answering the questions.